Hello, and welcome to the tutorial on building photonic circuits using the compact model library in Lumerical Interconnect. In this tutorial, we're going to build a Mach-Zehnder interferometer. The first step is to download the compact model library for Lumerical Interconnect, and this is available on the edX webpage. So download the file, it's a CML extension, and then we're going to start Lumerical Interconnect. Now in Interconnect, if you go to the element library, at the very bottom there's an item called Design Kits. So click on Install, and then find the compact library package that you just downloaded. So that's ebeam.cml. And then you have to choose a destination folder. So in my case, I'm going to put this on the desktop. Then push OK. And what you see is under Design Kits, now you have eBeam and then a list of all the components that are available in this compact model library. So we're going to start with a grating coupler. We're going to place two grating couplers, one for the input, one for the output. Let's flip the one on the right so it's facing the other way. Then let's add some Y branches. So one Y branch as a splitter. And then another Y branch as a combiner. Then let's add some waveguides. So these are 500 nanometer waveguides. The default is a length of 10 microns. So the second waveguide, let's change the length. And let's make this waveguide 100 microns longer, so 110 microns. Now we're going to wire up this circuit. Next, let's add an optical network analyzer to our circuit. And let's edit the properties. So first, let's change the plot to be wavelength. We can adjust the number of points in our plot. And we can also choose the range. So instead of gigahertz, let's change it to nanometers. And let's choose 80 nanometers as our wavelength span for the plot. Then let's wire this up so the output goes to the first grating coupler and the input of the network analyzer goes to the output grating coupler. Now let's run the simulation. And let's look at the results. So let's look at input 1 gain. And let's send this to the visualizer, so a new visualizer. And now you can see the interferometer spectrum. So now let's go back and remove the Y branches. What we're going to do is we're going to simulate this again, except with different splitters. And so go back to the design kit, and this time let's use the directional coupler. This is called the DC component here. So let's do port 1 of the directional coupler to the grating coupler, port 3 to the waveguide, port 4 to the waveguide, and let's duplicate this directional coupler. Let's put it at the output of the interferometer. And same thing. And the output of the directional coupler goes to the fiber grating. We can also adjust the length of the directional couplers if we want. Let's leave 15 microns. Then we run the simulation. And again, we look at the gain. And let's add it to our old visualizer so we can compare the response of the Y branch versus the directional coupler. So you can see the extinction ratio when you're using the directional coupler is not as large as with the Y branch. And also there's a wavelength dependence to the extinction ratio. You can see for longer wavelengths, the extinction ratio is increased. So now let's do this again. Let's delete the directional couplers And let's go with the adiabatic splitter, and let's wire this up again. This time, let's look at the output port, the second output port. And so we'll have a second fiber grating coupler. And in our network analyzer, let's add a second input. So we'll connect the second input to the second grating coupler. And now let's run our simulation. And let's look at the results. So now we have two inputs. So input 1 is the top port. Let's create a new visualizer. You can see the interferometer spectrum. And then let's look at input 2, which is the complementary output. And so you'd expect, in this case here, to see the opposite pattern. Anywhere you have destructive interference, you have constructive interference at the other port, and vice versa. So what's nice about these directional couplers and these adiabatic couplers is that they allow you to have two output ports, and this is obviously useful for making things like switches where you can route the light either to the top port or the bottom port. Now we can add these results to the other visualizer as well, so we can compare the three versions, the Y branch, the directional coupler, and the adiabatic coupler, and we can plot all the results together, and we can analyze these and compare them in terms of extinction ratio and so on. And this concludes the tutorial. If you have any questions, please ask below in the discussion.